Hi everybody, it's me Dr. V, and it's a great day to start reviewing for the AP Chemistry exam. Well, you've already started, of course. In this webcast, we're talking about 20 more common errors that we see on AP Chem free response questions, and more importantly, how to avoid them. The first common error that I want to talk about is SigFigs in calculations. Now, your teacher probably focuses on this a lot. We all do. But it was a real issue on the 2025 exam, question 3, part C, part 1. Let's go through this calculation. A student carries out a calorimetry experiment and records the data as shown in the table. Calculate the amount of heat Q released during the experiment in kilojoules. Assume that the specific heat of the solution is the same as that of water. So we know with these kinds of calculations, we're using our MC delta T formula, and delta T, of course, is T final minus T initial. We need to pay attention to that because it does affect the sign of our answer. For these calculations, we need to use the total mass of the mixture, so that would be 100.55 grams for this problem. And we have to calculate delta T, T final minus T initial, so we do 23.74 degrees Celsius minus 23.38 degrees Celsius. We get 0.36 degrees Celsius as our delta T. So we can take all of this information and put it into our MC delta T formula, substitute that in, and we get an answer on our calculators of 151.31 kilojoules. This is where students ran into trouble. The delta T that we calculated only has 2 SigFigs. Notice that the delta T has to be reported to the hundredths place because our temperatures were both reported to the hundredths place, and we're taking a difference there. And that means when we go to calculate Q and report it correctly with SigFigs, we need to report it with 2 SigFigs. Now, you don't know when you walk into the AP Chemistry exam which question is going to be scored on SigFigs. You do want to be paying attention to it, but most students missed the point for this question, not because they didn't do the calculation correctly, but because they didn't keep track of their SigFigs. So we have to report this as 150 joules. And this is where most students lost that point. It was a really difficult point to earn for most students, not because they don't know their SigFig rules, but because they lost track of them. We do need to finally convert this to kilojoules. The question did ask for it in kilojoules. In kilojoules, that'd be 0.15 kilojoules. Although if you left it in joules, you'd still get credit. So the common mistake here was reporting Q with too many SigFigs. This leads us directly into the second type of common error that we saw, is keeping track of the sign when you're calculating the enthalpy change from Q and the moles of the limiting reactant. So working through this same problem, continuing it on, the next part was to calculate the value of delta H in kilojoules per mole. Include the sign in your answer. You were explicitly told to do that. So we already know that Q was 0.15 kilojoules. That's the amount of energy that was absorbed by the solution. But we want to know what's happening from the perspective of dissolving the KOH. So we know that the enthalpy change from the reaction or from this process has the same magnitude, but the opposite sign of what the solution did. So to solve for delta H, what I have my students do is negative Q that they just calculated divided by the moles of the limiting reactant. And we do know in this problem that KOH was the limiting reactant. In other problems, you might have other information where you need to do that. But here we know it's all due to the moles of KOH. So we need to calculate the moles of KOH. We're told we have 1.50 grams. That's in the data table. We were conveniently given the molar mass of KOH. We're going to use that. We get 0.00267 moles. That would have 3 SigFigs. So to find delta H, I'm going to take my Q from the previous part, change its sign, divide by the moles of KOH. I get an answer of negative 56 kilojoules per mole. Again, notice I still only have 2 SigFigs. Now this all makes sense because the temperature of the solution did increase. That's telling us that this is an exothermic process, so the sign of delta H should be negative. But the common mistake that we saw here with this problem was students did not report that negative sign with their answer, and that's going to cost you the point. We don't want that to happen, of course. The next error that I want to point out is not finishing the calculation when it's a multi-step problem, stopping halfway through and not going all the way to the end of the calculation. For example, on 2025 number 1C, there was a calculation where you were given the molarity of a KOH solution and asked to calculate the pH of the solution in the beaker. So KOH being a strong base, that molarity is the molarity of the hydroxide ion solution. And so students knew to take the negative log of the hydroxide ion concentration, and they did that. And they wrote down an answer of 4.979. But that's the POH. That's not what the question's asking for. One thing I do want to point out here is that the hydroxide ion concentration has 3 SigFigs. So a pH or a POH from this should have 3 digits after the decimal, because those are the ones that are significant. I've not seen the College Board ask questions about SigFigs in pH calculations, but still, you should try to be careful about that. The common mistake that we were seeing here with this question is that students stopped here, wrote down 4.979, and recorded their answer as the pH. But it's actually the pOH. There was one more step you needed to do. You needed to remember that pH plus pOH add up to 14 when you're at 25 degrees Celsius. So the pH is 14 minus the pOH, or 9.021. And that's what you needed to write down here. So the other common mistake that often shows up with all kinds of calculations is just writing down an answer without any supporting setup at all, without showing how you got your calculation, not even the tiniest bit. Just writing down an equation is not enough. So you don't want to do that. Show enough work to support your answer. Another error that we saw frequently was in dilutions. You need to be able to solve dilution calculations correctly. So still in free response question number 1, there was a question where we mixed 2 solutions together, one containing calcium ion, one containing carbonate ion, and we're mixing these guys together. We want to calculate the concentration of the calcium ion after the solutions are combined, but before the reaction takes place, as if we could stop time. Assume that the volumes are additive. So if you don't know how to solve these problems, you're going to run into trouble. They're relatively easy to do as long as you know what to do. All right, the strategy that you really want to use here is M₁V₁ equals M₂V₂, because the moles of calcium before and after the dilution are going to be the same, and that's why this is a valid approach. This is not an equation that's on your formula sheet. It's one that you should know and be able to work with, though. So reading through the problem, all right, I've got calcium ion before and after. So my initial molarity of the calcium ion is 0.00345 molar. And it was originally in a 15.00 milliliter sample. And then I'm going to mix these 2 solutions together. And so what I really need to pay attention to, that I need to use V total, the total volume of the calcium solution and the sodium carbonate solution, which is 70.00 milliliters, and use that as V2. And then I can take my M₁V₁ equals M₂V₂ and rearrange it to solve for M2. So I can do that, and I can substitute my values in, and I should get an answer that's less than 0.00345 molar because I have diluted the sample. One of the common mistakes that we saw was that students were switching V1 and V2, so they were using the molarity of the calcium nitrate solution with the volume of the sodium carbonate solution, things like that. That's going to lead you to an incorrect answer. So make sure you're putting the right variables together. The other thing that we were seeing is that students, instead of using the total volume, they were using the volume of just the other solution as V2. That's not going to work as well. So we can substitute that in, and we get an answer of 7.39 times 10 to the minus 4th molar. And then we can talk about how to write KSP expressions. This was, again, an issue. So we're still really working through 2025, question number 1. The dissolution of magnesium hydroxide is represented by the following equation. So I have magnesium hydroxide, a solid, dissociating to form magnesium ions and hydroxide ions in solution. Just a KEQ expression, a particular situation, right? A KSP expression, which is what we're asked to write here. So my KSP expression would be the magnesium ion concentration times the hydroxide ion concentration squared. Equilibrium constant expressions, the rules are all the same, and yet we still often do see students making mistakes here. We don't want you to make those mistakes. So the common mistakes included leaving out the ion charges. Now, actually, if you put one in and not the other, you could still get credit, but really both ion charges needed to be there. You need to have those ion charges there. Another common mistake was not using square brackets. If you wrote parentheses here, you're not going to get credit for a KSP expression. If you included the solid, right? If you included the magnesium hydroxide in the denominator, you wouldn't get credit. This particular equation doesn't have any pure liquids, but if it had a pure liquid and you included it, you would not get credit. And if you don't use the coefficients from the balanced equation as the exponent, so if you don't write that the hydroxide ion concentration has to be squared, you're not going to get credit. So lots of places to lose credit here for what should be really a core skill. The next error I want to talk about is not using the information you were given or not being consistent with the previous answer to write your own response to the question. So we're still working through a version of the 2025 exam after the 2 solutions are combined in beaker 3 as described in the previous part. But before any reaction takes place, we're given a hydroxide ion concentration of 1.03 times 10 to the minus 5th molar. Using your answer from the previous part, calculate the value of the reaction quotient Q. Now think about it. At this point, we already know a KSP expression. We wrote that. We need to be consistent with that expression that we wrote in the previous part. We know a magnesium ion concentration of 7.39 times 10 to the minus 4th molar. And so we can substitute our hydroxide ion concentration that we were given and our magnesium ion concentration that we knew from our previous part and put that in. So we can calculate that. Lots of places where you could go wrong here, though. All right. If you didn't use the given value for the hydroxide ion concentration that you were given right here, that's going to lead to trouble. We actually had a lot of students saying, oh, well, I know the magnesium ion concentration and doubling that to get the hydroxide ion concentration. And if this were an ice table type of problem, that might be appropriate. But here, we're mixing the two solutions together. The concentrations are not dependent on each other. So we can't assume that the hydroxide ion concentration is twice the magnesium ion concentration. Use the information that you have. Or not using the magnesium ion concentration that you found in the previous step. Again, maybe thinking about that 1-to-2 ratio, or just coming up with a different number, or writing it down wrong. Lots of things to go wrong here. So sticking with this same problem, we can actually talk about another error, which is not calculating Q correctly. So we have the KSP expression. We have the magnesium ion concentration, we have the hydroxide ion concentration. So let's assume that we are actually using the right information here. But when we go to calculate Q, we do something wrong. So it should be the magnesium ion concentration times the hydroxide ion concentration squared. We get 7.84 times 10 to the minus 14. But the mistake that we're seeing, not squaring the hydroxide ion concentration, even though you had written it correctly in the KSP expression, squaring the magnesium ion concentration, right, not showing any work. You don't get credit with these kinds of mistakes. You do need to be consistent with what you had written before. So if your KSP expression was wrong, but you used it appropriately here, you're not going to get deducted twice for that same error. But you do need to make sure that, it's all consistent. The other error that we sometimes saw was students would label this calculation as K. But it's Q, it's the reaction quotient, it's my ratio right now, and it can change. K is fixed. So you can't call it K. If you called it K, you're not going to get credit. We can go on to our next error, which is incorrectly determining if a precipitate will or will not form. So these are Q versus K problems. There are lots of different varieties of Q versus K problems in AP Chemistry. But to solve this correctly, or appropriately, you need to compare Q, which you've already calculated, to the value of K, which you were given. I do want to remind you that K is a fixed value for that reaction as long as the temperature isn't changing. But what this all means is if Q is greater than K, that's saying that my ratio is too big, which means I have too many products. If I have too many products, the system has to proceed in the reverse direction. I need to make more reactants. And on the left side of the equation, of course, is my solid, so a precipitate would form in this case. If I do my comparison and Q is less than K, that's telling me that my ratio is too small. My ratio is too small because there are too many reactants. And that means I need to proceed in the forward direction and make more products and use up some of my reactants. And in that case, since I'm making more products and the products are ions in solution, no precipitate would form. So we have a reaction quotient that we've already calculated. We know a value for K, which we were given, and we need to compare these two values. The thing I want to point out to you is you need to look at the exponents first and not the coefficients, all right? So the given KSP value is 10 to the negative 12th. Our Q is 10 to the negative 14th. That's way smaller than the K. So Q is less than K. The system's going to proceed in the forward direction. I'm not expecting a precipitate to form. So one of the common errors that we saw is students didn't explicitly compare Q to K somewhere in their answer, whether they're comparing the numbers or, less than, greater than, something along those lines. But then also not looking at the numbers appropriately. If you compared the coefficients and not the exponents, you're going to incorrectly compare Q to K, right? 7.84 is larger than 5.61, but this is scientific notation, and you need to take that into account. The other error that we would see is students would correctly compare their Q value to their K value for the numbers that they had, but then telling us that it's going to do the wrong thing and not interpreting that information correctly. So lots of places to make mistakes here. The next area I want to talk about is Coulomb's law. You need to correctly identify the particles that are interacting. Still in free response question number 1 from the 2025 exam, explain why, using Coulomb's law, a sodium ion, Na+, has a weaker attraction to water than a magnesium ion does, based on the relative radii of the ions. So Coulomb's law, we know there are two things that affect the strength of that attraction, right? It's the charge magnitude of the ions and then also the distance between the particles. And this part is really focusing on the distance between the particles. And that's what you have to talk about in your answer to a question like this. The interparticle difference from the center of the ion to the center of the oxygen atom, because that's what's going to be attracted to the cation. So the common mistake that we saw here when scoring these questions was that students talked about why the radius of the sodium ion and the radius of the magnesium ions were different. So they were discussing the attraction between the nucleus of the ion and the outermost electrons of the ion. And that's not really what this question is about at all. What you needed to talk about was that the magnesium ion has a smaller ionic radius than the sodium ion. Just saying that, however, was not enough. If we put them side by side, just thinking about our periodic trends, we do expect the sodium ion to be larger in radius than the magnesium ion. The why of that is not really what's important here, but the fact that the radii are different. And so as the water molecules come in and start interacting with the ions, right, the oxygen portion of the molecule, which is partially negative, is going to be attracted to the cations. So we need to look at the distance between the nucleus of the sodium ion and the nucleus of the oxygen atoms in the water. The distance between the magnesium ion and the oxygen atom in water, or those internuclear distances, is shorter than the distance between the sodium ion and the oxygen atom in water. And that's the gist of what you needed to talk about. I do want to point out that the oxygen atom is a partially negative oxygen, right? It's a polar molecule. There's a little extra electron density around the oxygen because of those polar bonds and it being a polar molecule. But it's not an ion. It's not a -2 ion. And if you talked about that in your response, you're not going to get credit. So you want to be very careful. But it's really important that you specify which particles are interacting when you're doing Coulomb's law questions. Error number 10, what makes isotopes different from each other? So for example, the element copper has 2 isotopes, copper 63 and copper 65, and we've got a mass spectrum here. Describe the difference in atomic structure that accounts for the difference in mass between copper 63 and copper 65. And all you needed to say was that copper 65 has more neutrons than copper 63. You could say that copper 65 has 2 more neutrons than copper 63. That's fine. But the gist of your answer had to be different numbers of neutrons. Common mistakes that we saw, we had lots and lots of students talking about them having different numbers of protons or different numbers of electrons. If you just said they had different mass numbers, that doesn't talk about atomic structure, so that's not specific enough. We also saw a lot of students talking about incorrect numbers of neutrons. So if you said copper 65 has 65 neutrons and copper 63 has 63 neutrons, well, that's not correct. So you didn't get credit for that either. Should have been an easy question, and a lot of students really struggled to answer this. Buffer calculations. Students always get lost in buffer calculations, and I think students tend to overcomplicate it. So let's start by just reviewing really quickly what a buffer is. All right, a buffer system is formed when you take a weak acid and combine it with an ionic compound that contains its conjugate base. You have a conjugate acid-base pair for a weak acid. Or you can have a weak base and a salt containing its conjugate acid. Either way, it's a conjugate acid-base pair for weak acids and bases. I think and strongly believe that the best strategy for solving buffer problems is to rearrange the Ka expression to solve for whatever it is you need. If you need the pH of the buffer, rearrange it to solve for the H+ concentration, and then you can take the negative log of that. I recommend avoiding the Henderson-Hasselbalch equation. Yeah, I know it's on your formula sheet, but you know how to write Ka expressions. And I actually think it's a lot more flexible to rearrange your Ka expression to get what you need, rather than trying to rearrange the Henderson-Hasselbalch equation to get what you need. Because the Henderson-Hasselbalch is really just derived from the Ka expression anyway. That's my advice. That's what I'm sticking to. Let's do a quick problem and show you what I mean. So in 2025, there was a question very similar to this, question 2a. When dissolved in water, lactic acid establishes an equilibrium. So the lactic acid dissociates to a small extent to make hydrogen ions and the lactate ion, and we're given a Ka value. A buffer was prepared by combining solutions of lactic acid and sodium lactate. So we have a weak acid and its conjugate base. It's a buffer. The question is, what's the value of the ratio of lactate ion over lactic acid when the pH of the solution is 3.50? And you're like, oh, what do I do? Go back to your Ka expression. Let's rearrange it. So we know a Ka expression. You can easily write one. You have the balanced equation. If you didn't have one already, go ahead and write it. But that ratio is right there. It's pretty easy to rearrange the equation to solve for just that ratio, and that's equal to the Ka value over the hydronium ion concentration, or the H plus concentration. They're interchangeable, right? And we know the Ka value. We were given that. And we know the pH. So from the pH, we can find the hydronium ion concentration. That'd be 10 to the negative pH. So we can substitute that in. We get a hydronium ion concentration of 3.2 times 10 to the minus 4th molar. So we know the Ka, we know the hydronium ion concentration, we can substitute that in. I get a ratio of 0.43, and we're done. It's really not that hard. If you try to do it from Henderson-Hasselbalch, it was very complicated. So much easier this way, so much more flexible. I also want to point out that this answer makes sense. If we calculate the pKa of this acid, the pH of this buffer is less than the pKa, so it makes sense that my weak acid concentration is greater than my conjugate base concentration, giving me a ratio that's less than 1. The common mistakes that we saw with these problems were rearranging the expression incorrectly. If you chose to do Henderson-Hasselbalch with this, and you make a mistake, you might not find that for a bit. Not converting your pH to H+, not taking a pKa and finding a Ka, things like that, depending on what information you're given. The next area I want to discuss is not providing enough information when you're talking about the method of initial rates. Here's a typical problem. A student is studying the kinetics of a reaction. There are two reactants, A and B. The student runs 3 trials of the reaction with different initial concentrations of both A and B. The data is here in the table. The rate law for the reaction is given as the rate equals K times B squared, second order in B. Explain how the data in the table support the conclusion that the reaction is second order with respect to B. You need to make sure you give enough information here. You need to tell me, what trials are you comparing? What's being held constant? What's being changed? How is the rate affected because of this change? I'm actually going to give you a sentence frame or a series of sentence frames to use. Comparing trials, what's held constant, what's changed by what factor, how does the rate change by what factor, and therefore the reaction is blank order with respect to that substance. So let's use that for this answer. A thorough answer says, comparing trials 1 and 3, the concentration of A is held constant. The concentration of B is doubled. The rate changes 4-fold. Therefore, the reaction is second order with respect to B. The next area I want to discuss is overlooking the hydrogen to oxygen element ratio when you're doing combustion analysis problems. Now, these really are just empirical formula problems. They've shown up several years in a row, so you want to make sure you can do them. But for combustion analysis specifically, you want to pay attention to this. So if you have the grams of CO2, you can find the grams of carbon and therefore the moles of carbon. So if we have the grams of water, we can find the moles of water. And then if we multiply that by 2, that gives us moles of H. It's really important that you remember that there are 2 H atoms for every H2O molecule. So the moles of H atoms is twice the moles of the water. And then you divide by the smallest number of moles. And if they're still not whole numbers, you multiply until you get whole numbers. Here's a question inspired by question 2A from the 2025 exam. A 1.50 gram sample of a hydrocarbon undergoes complete combustion to produce 2.20 grams of carbon dioxide and 1.35 grams of water. What's the empirical formula of the hydrocarbon? Because we know the mass of CO2, we can use that to find the moles of carbon. So we can convert our grams of CO2 to moles of CO2, and then the moles of carbon and CO2 are the same. So we get 0.0500 moles of carbon. For the hydrogen, to find moles of hydrogen, we need to take our mass of water and convert it to moles. And then we need to remember that there are 2 moles of H for every mole of H2O. And so when we do that, we get 0.150 moles of H. We need to divide by the smallest number of moles, which is 0.0500. So my moles of C is 1, and my moles of H is 3, in terms of my lowest whole number ratio. But the common error that I see here is students forget to multiply the moles of H2O by 2 to find moles of H. That's the number one mistake they make. The other one is then not dividing by the smallest number of moles. When you do it correctly, you get an empirical formula of CH3. The next error I want to talk about is not counting the particles when the problem involves particle level diagrams. The question was inspired by something from the 2025 exam, but let's talk through it. It doesn't really matter what topic area the particle level diagram is about. What's important is you count particles, because if you don't count particles, you're not going to answer the question correctly. A particle level diagram of an equilibrium mixture of AlCl3 and Al2Cl6 at 400 degrees Celsius in a 25-liter closed container is shown. And we are also given the equation for the reaction. The question asks, if each particle in the diagram represents a partial pressure of 0.10 atmospheres, what's the value of Kp for this equilibrium mixture at this temperature? Well, the first thing we probably should do is count particles. What I see right away is that there are 7 AlCl3 molecules. And I have 3 Al2Cl6 molecules. Always count them. Why? This is going to be really helpful. I need to calculate a Kp value. So a Kp expression is always written in terms of pressures of the gases. So products over reactants. So PAl2Cl6 divided by the pressure of the AlCl3 squared, because it's got that coefficient of 2. But I know that each particle represents 0.1 atmospheres. So that's telling me that the partial pressure of the AlCl3 is 0.70 atmospheres. And the partial pressure due to the Al2Cl6 is 0.30 atmospheres. So I can now substitute these values into my Kp expression, and I get an answer of 0.61. But if I hadn't counted the particles, I wouldn't have known what numbers to put in. Always count your particles. The next error I'd like to discuss is incorrectly predicting shifts in the equilibrium position using Le Chatelier's principle. And I think a quick review here might be helpful. What I want you to keep in mind is whatever you do to the system will try to undo. That's really what Le Chatelier's principle is all about. If you add reactants, the system's going to use up those reactants and make more products. That means Q is now less than K, and I'm going to proceed in the forward direction to reestablish equilibrium. If I added products, I'm going to use up the products and make more reactants. What I'm saying is that Q is now too big compared to what K should be. I'm going to proceed in the reverse direction, or shift left, to reestablish equilibrium. If I'm removing things, if I'm removing products, I'm going to use up reactants and make more products, and I'm going to proceed in the forward direction. And if I'm removing reactants, the system's going to use up products and make more reactants, and I'm going to shift left or proceed in the reverse direction to reestablish equilibrium. If you've got gas phase systems, you might be, say, reducing the container volume, and that means the partial pressures of each gas is going to go up. And as a result, the system is going to proceed in the direction that will relieve the stress. If the pressures have gone up, I'm going to go to the side that has less pressure, which would be the side that has fewer moles of gas. If I increase the container volume, I'm going to do just the opposite. The partial pressure of each gas is going to decrease, and so in order to compensate, I'm going to go to the side that exerts a higher pressure, which would be the side of the reaction that has more moles of gas. So we can use this to really make all of our Le Chatelier's principles predictions that we need. Here's a problem based on the 2024 exam, question 5b, part 2. The reaction is hydrogen gas plus iodine gas makes 2HI. We're given an enthalpy change for the reaction of negative 12 kilojoules per mole. A student monitors the number of moles of HI over time. Hypothesize an experimental change that could have been applied to the system in the rigid container at time t to result in the change in the number of moles of HI shown in the graph. Assume that the student did not just add more HI to the system. Well, looking at the graph, we had been at equilibrium, and at time t something happened, and after time t, my moles of HI went up. The moles of HI increased, and if I look at my reaction, HI is a product. So I'm trying to make this system shift right. Because of this stress, the system made more products. I need a stress that's going to shift the equilibrium to the right. So I've got a couple of options. One option could be that I add more reactants. So I could have added more hydrogen gas. I could have added more iodine vapor. Alternatively, another way I could answer this question is I could have said I lowered the temperature. The reaction is exothermic, which means the energy term belongs with the product. So if I lower the temperature, it's kind of like I'm removing products, even though I'm not really removing products, but because I'm lowering the temperature, I'm going to shift right to compensate. So I have 3 different ways I could answer this question. Here's another example of Le Chatelier's principle shifts and making sure you can do them correctly. If the temperature of the system is increased, so we're back to our AlCl3, Al2Cl6 equilibrium, and we're given a delta H of the reaction. If the temperature of the system is increased, keeping the volume constant, will the value of the equilibrium constant increase, decrease, or remain the same? Justify your answer based on the value of delta H for this reaction. So we know that delta H is negative. So it's like thinking about the energy term as a product, right? It's not technically a product, but it belongs on the product side when we think about it as a thermochemical equation. And so if I increase the temperature, I'm going to preferentially speed up the reverse reaction. It's like I'm adding product, and I'm going to shift left as a result. All right, I'm going to proceed in the reverse direction. I'm going to make more reactants. And if I make more reactants, when I think about my KEQ expression, whether it's a KP or a KC doesn't really matter here, I'm going to be making more reactants, which means my denominator is going to have a larger magnitude. And as a result, in this situation, the K would decrease. I do want to remind you that only temperature changes are going to result in a change in the value of KEQ. Error number 16. Talking about disorder when you're trying to explain entropy changes for a reaction. The College Board will not accept that. If you want to explain entropy changes, start by stating the moles of reactant particles and their states of matter. State the moles of product particles and their states of matter. And then talk about whether the available microstates increase or decrease as a result of the reaction proceeding. You could also talk about dispersal of matter, but under no circumstances should you be talking about disorder. It's not going to be accepted. Are there more possible arrangements of particles or fewer possible arrangements of particles related to the number of moles and the states of matter? And I want to also remind you that if the question asks for a particle level explanation, you really need to put the word particles in your response. Let's do an example. A chemical reaction between maleic acid and sodium bicarbonate occurs in the presence of water to produce carbon dioxide and sodium malleate as represented by the following equation. And here we go. The reaction has a value of delta S that's greater than 0. Using particle level reasoning, explain why the entropy increases as the reaction progresses. We really want to use our format here, right? It specifically says particle level reasoning. So the reactants have 4 moles of aqueous reactant particles. The products have 2 moles of gas particles and 3 moles of aqueous or liquid product particles. So going from 4 moles to 5 moles total, and I'm going from things in solution to things in solution and 2 moles of gas. The 2 moles of gas that are produced have a lot more available microstates. So I've got more moles, I've got a state of matter that inherently has more possible arrangements, and so the products have a higher entropy than the reactants, right? Compare my reactants, compare my products, states of matter, number of particles, and talking about available microstates. I could also talk about greater dispersal for the gases, right? I tend to talk about available microstates. That's usually my preferred wording. The next error is confusing endothermic and exothermic changes and what that does to temperature. With an endothermic process, what we observe is that the temperature of the surroundings decreases. But in an exothermic reaction, the temperature of the surroundings increases. The reaction of an endothermic reaction is absorbing energy from the surroundings, so the temperature of the surroundings drops. Whereas in an exothermic reaction, the reaction or the system is releasing energy to the surroundings and their temperature goes up. Thinking about this graphically, in an endothermic reaction, we're going to see a temperature drop. In an exothermic reaction, we're going to see a temperature rise. You can also think about this in terms of potential energy diagrams. Endothermic reactions have a positive delta H value. Exothermic reactions have a negative delta H value. In terms of our potential energy diagrams, the products in an endothermic reaction have a higher energy than the reactants. And in an exothermic reaction, the products have a lower energy than the reactants. So keeping all of this together, we need to be able to talk about this. But these are things that students commonly get confused. For example, in the 2023 exam, question 3F, talking about the reaction between calcium carbonate and hydrochloric acid. The student's trying to measure the enthalpy of the reaction, and they mix 50 mils of HCl with 1 gram of calcium carbonate in a coffee cup calorimeter. The student records the temperature of the calorimeter contents every 20 seconds, and the data are shown here. The question is the reaction endothermic or exothermic? Justify your answer using the information in the table. Well, we start at 21.20 degrees. 20 seconds later, we're at 21.50, and then we eventually get up to 21.90 degrees. The temperature went up. The reaction is exothermic. Our justification is that the temperature of the solution increases as the reaction proceeds. But the common mistake was just saying it was exothermic and not relating it to the data. Right? They might talk about entropy, talking about all kinds of things, but not saying that the temperature went up as the reaction proceeds. That's what you had to do. Another error that we see a lot, students will confuse catalysts and intermediates when they're discussing reaction mechanisms. Just as a quick refresher, a catalyst, in terms of a mechanism, is consumed in one step and regenerated in a later step, whereas an intermediate is produced in one step and then consumed in a later step. Neither of them are going to show up in the overall balanced equation. But you need to know what the sequence is. For example, in this little particle level diagram, I have a catalyst, which is the little blue dot. And then the intermediate is the blue with the purple. All right. So the catalyst is made in step 1. I get it back in step 2. The intermediate is made in step 1. I use it in step 2. Consider the reaction mechanism shown here. A student claims that species Y is a catalyst. Do you agree or disagree? Justify your answer based on the mechanism given. So if you look at the mechanism, in step 1, Y is a reactant. And then in step 3, it's a product. So I agree that Y is a catalyst in this mechanism because it's consumed in step 1 and regenerated in step 3. Some of the common mistakes are discussing that Y doesn't appear in the overall equation, but that doesn't tell us it's a catalyst. Another common mistake was defining catalyst in terms of the effect on the reaction rate, but not talking about its role in the mechanism. Another common mistake was contradicting yourself, agreeing that yes, Y is a catalyst, but then giving an incorrect explanation from the mechanism. Here's another question you could get asked, all right? Identify, same mechanism, identify an intermediate in this mechanism, justify your answer based on the mechanism. So for an intermediate, we need something that's formed in one step and it's a reactant in another step. So I'm going to argue that X is an intermediate because it's formed in step 1 and it's consumed in step 2. We could also argue that XY is an intermediate. I form it in step 1 and I use it in step 3. Either one would be fine. All right. So common mistakes would be discussing that X doesn't appear in the overall equation. Again, just like with catalysts, that doesn't tell us it's an intermediate. You're not explaining your answer in terms of the mechanism. You're not telling us what's happening in step 1 and what's happening in step 2, or whatever steps are relevant for the intermediate you chose, since there's more than one. Identifying the intermediate, but then explaining why it's an intermediate and doing that incorrectly. So you want to not do that. Next error I want to talk about is incorrectly relating Gibbs free energy, delta H of reaction, and the entropy change of a reaction. Key points to keep in mind. If the reaction occurs on its own without any intervention, like you mix the two things together and that reaction happens, that's a spontaneous reaction, thermodynamically favorable. We know that delta G is a negative value. If the reaction is exothermic, we just reviewed this, delta H is negative, and that's favorable. That makes a reaction more likely to occur. If the total moles or the moles of gas increase, we're probably going to have a positive change in entropy, and increases in entropy are also favorable. Remembering that spontaneous reactions have negative delta G is a really helpful thing. I also want you to be able to talk about the Gibbs free energy equation and relate it to the signs of delta H and delta S. You need to really know these relationships and be able to do calculations with them as well. But conceptually, this is where students run into trouble. So if delta H is negative and delta S is positive, delta G will always be negative. That reaction will always be thermodynamically favorable at any temperature. It doesn't tell us if it's fast or slow, just gives us the sign of delta G. If delta H is positive and delta S is negative, delta G will be positive. That process will be not thermodynamically favorable at all temperatures. So when the sign of delta H and delta S are different, we can unambiguously predict the sign of delta G. When delta H is negative and delta S is negative, it's an indeterminate situation. It depends. At low temperatures, the reaction will be thermodynamically favorable because it's enthalpy driven and that T delta S term is small enough that we still get a negative delta G. At high temperatures, we're going to get a sign change for delta G because we have a big enough T delta S term that now when we subtract it, we're going to end up with a positive number. When delta H is positive, which is not favorable, and delta S is positive, which is favorable, again, we have another indeterminate situation. In this case, the process will be thermodynamically favorable at high temperatures. It'll be entropy driven at high temperatures, but not favorable at low temperatures because the delta H term is positive, but I'm subtracting a very large T delta S term, big enough that I end up with a negative delta G at those high temps. So you need to know this table and be able to work through it. Let's do a quick practice problem inspired by 2016 number 2D. So we're going to react an acid with sodium hydrogen carbonate. We get CO2 and H2O and a salt. Considering that the flask gets cooler as the reaction proceeds, what drives the chemical reaction between this acid and the sodium hydrogen carbonate? Answer by drawing a circle around one of the choices below. The choices are enthalpy only, entropy only, or both enthalpy and entropy. And then justify your selection in terms of delta G. So looking at this reaction, first of all, we are told that the flask gets cooler. The temperature drops. And that means that delta H is positive. Remember, this is one of those common errors students make. Looking at the balanced equation, I see that I predict that we're going to have a positive change in entropy, which is favorable. I have an unfavorable change in enthalpy, but a favorable change in entropy. So I'm going to say that this reaction at these conditions is driven by entropy only, because the entropy change is favorable, right? I have a positive change in entropy because I'm making gas. I want to justify this in terms of delta G. Well, when I mix these two things together, the reaction occurs. So that tells me that delta G is negative. Because the temperature drops, we know that delta H is positive. That's not favorable. Because of the 2 moles of gas produced, we know that the entropy change is greater than 0. That is a favorable change. So thinking about the Gibbs free energy equation, right? Delta G equals delta H minus T delta S. I have a positive value for delta H, and I have to subtract that T delta S term. And we know that delta G is negative. It must be because the magnitude of the T delta S term is large enough that when I subtract it from my positive delta H term, I still get a negative number. And this is really what we needed to talk about. So the common mistake that students make here was literally predicting the wrong sign for delta H, but then not backing that up correctly in terms of delta G and delta H and delta S and how all those signs tie together, right? Because delta H and delta S are both positive here. It's a temperature-dependent situation. The last type of error that I want to talk about is intermolecular forces. Students struggle to identify what types of intermolecular forces are involved. And when you're doing this, you have to ask yourself, what do we know about the interacting particles? Are they both nonpolar? In that case, we're talking about London forces, attractions caused by temporary or induced dipoles due to uneven electron distribution. All matter can participate in London forces, so it doesn't have to only be 2 nonpolar species, but they're most important when it's a nonpolar species. The essential vocabulary term you want to keep in mind when you're talking about London forces is polarizability. A bigger electron cloud means that electron cloud is more easily distorted, and it's easier to polarize it, and therefore the London forces will be stronger. If the interacting particles are a polar molecule interacting with something nonpolar, that's a dipole-induced dipole attraction. So if a polar molecule approaching a nonpolar species, inducing a temporary dipole in the nonpolar species, and now you have oppositely charged regions that can be attracted to each other. If the interacting particles are 2 polar molecules, so they're both permanent dipoles and they always have a partial positive end and a partial negative end, now we're talking about dipole-dipole attractions. So we have a partial positive end of one, partial negative end of the other. They're always going to have these are partially positive and partial negative end, and they're attracted to each other. That's a dipole-dipole attraction. We can have ions interacting with polar molecules. These are ion-dipole attractions, and I want to point out that the oppositely charged end of the polar molecule is what approaches the ion. For example, here are water molecules surrounding a chloride ion. Notice it's the pink hydrogen atoms in this representation that are approaching the chloride ions because they're partially positive. And surrounding a sodium ion, notice it's the blue oxygen atoms in this representation that are approaching the sodium ion in these ion dipole attractions. I did not make these really cute little animated GIFs. They came from dynamicscience.com, but they're great. The one thing I want to point out about this is it makes it look like the chloride ions and the sodium ions are the same radius, which would not be true. I would expect the chloride ion to be substantially larger in radius than the sodium ion. The last type of IMFs are hydrogen bonding. So in a hydrogen bond, you have an H atom bonded to an N, O, or F atom. And that hydrogen atom is attracted to another molecule's N, O, or F atom. Just because a covalent bond has a hydrogen in it does not mean that that substance is going to be able to do hydrogen bonding. I also want to remind you that hydrogen bonds can form between 2 of the same kind of molecule, or they can form between 2 different kinds of molecules. So this one is a hydrogen bond showing between a water and an ammonia molecule. So we have an H bonded to an O, and it's attracted to the N of the ammonia. And that very strong attraction, that very strong IMF is called a hydrogen bond. The term's a little misleading, but we got to run with it. That's what they're called. Make sure you know the definition, because if you don't know the definition, you can't apply it. In 2023, question 6A asked us to list all the types of intermolecular forces present in pure samples of liquid HBr and liquid HF. What I want to point out right away is that both HBr and HF are polar molecules. Since they're both polar molecules, they can both do London forces. Of course, all matter can do London forces. They're polar, so they can both do dipole-dipole attractions. And so for HBr, that's what we needed to list, London forces and dipole-dipole attractions. For HF, though, they can do London forces and dipole-dipole attractions, and they can hydrogen bond to other HF molecules. So we want to make sure we can list them all. Another thing that we can be asked to do in terms of hydrogen bonding is to draw where they would form between two molecules. So this is from the 2025 exam, question 4B. And we've got a sample of methanol molecules and a sample of formaldehyde molecules. And we want to draw a single dashed line to represent a strong hydrogen bonding attraction between one methanol molecule and one formaldehyde molecule. Now, thinking back to our definition, we need an H atom bonded to NO or F. So I'm going to highlight them in pink. There are only two hydrogen atoms that are bonded to NO or F, and they're both in the methanol molecules. So they're in pink. And they need to be attracted to another molecule's NO or F. Now, there aren't any N's or any F's in these molecules, so it's all about the O's. So I'm going to highlight the O's in other molecules, and I'm highlighting them in blue. You need a strong attraction between a highlighted H and a O. In order to do that, right, I do need to think about proximity. If they're too far away from each other, or they're not angled, or I have to draw it around things, that's not going to work. The proximity is important, and because of that, there's really only one location in this drawing where I can draw a hydrogen bond, and that's between the hydrogen and the oxygen in the bottom right-hand corner. All right, so I've got my series of dots there to draw my dash line. You don't want to draw more than one line, because if one of your lines is wrong, now you get no credit. All right, you do want to make sure your dash line is between a methanol molecule and a formaldehyde molecule. You were specifically told to do that in this question. I want you to keep studying chemistry every day. If you found this video to be helpful, like the video and leave a comment, and subscribe to my channel so you get all my latest updates, tips, and advice for the AP Chemistry exam.